Hello, everyone. My name is Zirui from National University of Singapore. I'm very happy to be invited here to share my recent research that's combining large language models into algorithm to solve the large-scale task planning problem. Consider about you have, for example, like you have a robot in your house, and you can, tell him anything to do something for you, right? For example, I would like to have some fruits, and I want the robot to satisfy me. Now, it seems to be a bit simple for humans to do this kind of things, but actually for robots, if you want to if you really want to have the robot in your household environments, that's not be an easy problem. And first of all, is that our real world is actually a large domain, right? Consider your house. There will be hundreds, even thousands of interactive objects. And that is going to be a very large domain because each object will have its unique states, its position, its property, its color, etc. Those kind of things will define a very large state space. And second is the partial observations, right? This is a very typical problem if you want to consider a real robot in your house, right? We can only observe the objects around us. That means we can only have the partial information about the states. Okay, we can only know a part of the information about our house. So that is actually another challenging problem. How can we do a planning under the uncertainty of the environments? And we need to also consider about, if you want to solve this problem, I want to have some fruits. I need to execute multiple actions to achieve the goal. That requires me to reason over a long time horizon. And if you consider all these three factors, if you have a large domain and you want to solve the problem by a classical search algorithm, then it will becomes a very large search tree because a large domain will have a very wide tree and long planning horizon will have a very deep tree. So that is going to be a long, deep and also wide search tree and make the planning intractable. So in this paper, we aim to solve this kind of large-scale planning problems by using the large language models together with the search algorithm. Right. So there have been a lot of research that focusing on how can we use large language models to solve the planning problem. So one type of research is that I can use large language model directly to plan for me, or is not plan for me, to generate a plan for me. Right. For example, I want to have some fruit, please. And I will tell him that any prompts, for example, like that, let's do it step by step, and some other information is in the prompts. And the large language models will just output the actions to execute that directly tell me how to do this without any, search procedures. So this type of solution is called using LLM as a planning policy. So that directly tell me the answer. Right. So this is called a policy. But directly using LLM will have a lot of difficulties, especially if you want to apply an AI agent in your real world. For example, like LLM may, make some hallucinations, right? Produce something very confidently, but it's something wrong. So that is going to be really risky if you have a real robot in your house and you cannot control it from making mistakes. You have no idea about why the robot will make that kind of mistakes. That is something that we will not want to. So another type of idea is that maybe we can use LLM as a type of, a simulator of the worlds, or we say it's a world model, right? So consider about when we do planning, we will do planning in our minds, and we close our eyes to imagine, okay, if I want to have some fruits, I will, first go to the kitchen, and if I go to the kitchen, what I'm supposed to observe is, for example, like a fridge, and so on and so forth. So that kind of things, we have a world model in our minds. And the similar idea is that we can use a LLM as a world simulator so that we can apply some actions and receive the feedback accordingly. So that I can run a search algorithm, which is safe. We know what is happening there, and we also know what is going on afterwards. Right, so this kind of things will have a very strong advantage compared with using LLM as a policy. But the problem here is that it will not be able to solve the large scale problem. as we have said that if we want to use LLM if we just directly use a search algorithm to solve it, then it's going to be very difficult because it's an intractable solution. So the problem here is that can we take advantage of both sides, right? So can we benefits from the both sides, right? Leveraging the LLM as a policy as an advantage, but also control it by the algorithm, right? So this is our main idea. So can we put those two things together in the planning algorithm so that we can benefit from the policy, right? We have some common sense about how to solve the problem, and also control it in the planning algorithm, and that's regularized by using LLM as a world model. So together. So in this problem, in this paper, we formulate the problem as a partially observable Markov decision process. So that means which is a very special and more difficult version of MDP. So in the POMDP, we have to define several things. We have to define the state space, action space, and observation space. That means the state means how the world will be like and where are the objects. And the action means that the robots can interact with the objects. For example, like pick up the object, put the object on the table, and navigate around the room. And observation means that if you execute an action, you will observe something, right? So, for example, if you enter the kitchen, you will observe there is a fridge, there is a food, etc. And this kind of things are observation here. And in addition is that we probably need to have, how can we interact with the real worlds? How can we interact with the environments? Is the state transition function. That means if I apply some actions to the current state S, and then my state will transit to the next state, which is S prime. For example, I pick up the apple and put it to the microwave, then that means the state of the apple is changed. And the observation function means that if I apply some action in the current states, I will receive some new information. So what is the probability of, given the current states and also the action, my observation will be like? For example, I have a high probability that if I go to the kitchen, I will receive the observation that I can see the fridge. Right? So there's a high probability like this. And the reward function here is that we need to define the object planning objective, right? So we want to achieve something, right? So which is defined by the reward function, right? For example, if I finish my task, I will receive a high reward signals, and otherwise I will receive a small penalty for not achieving the goal for every single step. So then is my objective. My objective is always to maximizing the accumulated rewards at each time steps. So that is a POMDP planning problem. So given that kind of things, and how can we execute the sequence of actions so that I can maximize the expected rewards? Since we do not have because in the POMDP that have one very strong assumption is that we have no idea about the perfect information of the state S. So that means we can only have estimation of the states, which is represented by the probability distribution, which is BS. We call it as a belief, right? So for example, like in the house, in a new house that we have never visited before, I will have a probability distribution over my state. For example, like where is the kitchen, where is the fridge, where is the foods? The foods supposed to be in the kitchen, and the dishes are supposed to be in the kitchen and the dining room, and the bed is supposed to be in the bedroom. So that kind of things can be formulated as a probability distribution over the position of objects, right? So the position of the apple is more likely to be in the kitchen, right? So this kind of things. So which can be formulated as a distribution. And if we want to plan in the POMDP, we usually represent it as a belief search tree. Right? So in the roots of the tree is a belief of states, and in each branch will have these branches by the nodes are branches by the selected actions. For example, I can choose to enter the kitchen, I can choose to enter the living room, I can choose to enter to the toilets. And those are different type of actions that can branching my results. And after I execute one action, I will receive a new observation because I have no idea. I do not have the perfect information about the states, so I can only estimate the states from my observations. Right. So, for example, if I enter the kitchen, I will more likely to observe that there is a fridge, there is a food, there is a microwave, etc. So those are observation branches. So we can take all the possible actions and all the possible observations together, so that it's going to be a belief search tree. And for example, if I want to have some fruits, then I can select the action, so go to the kitchen. And after I go to the kitchen, I may see the fridge. And then I can select another action and so on and so forth, receive a new observation. So this kind of things will put all the possible actions and all the possible observations together. It's going to be a belief search tree. And our objective is to recursively achieve our ultimate goal, which is to maximize the overall, maximize the accumulated reward over time, which can be computed recursively using this to compute this by a value function, which is it seems to be a bit complicated, but all the things that you need to know is that it is a recursive algorithm. We select the branches of the actions, and then we apply the observation according to the probability distribution, and then we then put this into another subtree and do the same thing, and so on and so forth. After that, after we reach the leaf of the tree, we will put all things together and go back to the roots, so that it can recursively updates until it find out the optimal thing. But as you can see that if for our problem, there is a large state space, a large action space, and partial observations, as well as a long planning horizon, this tree will be very large. And to compute this kind of things will be very, very difficult if you want to directly compute it. And a very typical algorithm to solve this is to use Monte Carlo Tree Search. So the Monte Carlo Tree Search means that I will not going to directly compute the recursive Bellman equation, but I want to use the sampling-based methods, right? Or I will sample the states from the roots and sample the observation, and so on, sample the action, sample the observation, so on and so forth. I have approximation of this tree, and so that I can solve this problem in an approximate way. And this approximation will have a, it's a good enough, even though it's not optimal, but it's good enough for me to solve this problem. And it's an anytime algorithm. If you stop executing at any time step, it will produce you the optimal solution at that time. So the algorithm is that from the belief search tree, I will first select the action branches until I reach the leaf nodes. And after that, I will sample the new observation, and also I will sample the next step. After that, I will have a simulation, which is to say I have a rollout policy. I will try some random actions until the timeout or until the task is finished, and then I can have a reward that was received over time. So that kind of things will be returned to each state nodes, and it will update the estimated Q function. The Q function means it's the expected reward that if you apply some action at some states. Right, so this is the estimated Q function because I will run some random sampling over the trajectories, and then I will output some averages of my return. And after that, if I go back to the roots, and then at my roots, my estimated Q value will be updated over time. And after a reasonable long time horizon, my estimation will be more accurate. Right, so this is the definition of Q function, which is the expected reward received if I apply some action A at the state T, at the state ST. Now let's go back to our problem, which is to combine the world model together with the policy into the Monte Carlo Tree Search. But how can we put them together into the Monte Carlo Tree Search? Which is something very straightforward. So imagine that you want to solve the problem of, give me some fruits. And imagine I want to solve it, and I will go to the kitchen first. And before I go to the kitchen, I will think about that in my mind, right? So before I go to the kitchen, when I do the planning, I will think about, oh, okay, I want to go to the kitchen. And if I go to the kitchen, what am I supposed to observe, right? So if I do not have any common sense knowledge, I have no idea about the common sense knowledge in our worlds. And then I will say, okay, this is possible to see anything, right? For example, I can see the fridge, I can see the pots, I can see the plates, or I can see the toothbrush, shampoo, etc. Or I can see the laptop, books, etc. Things like this, right? So if I do not have any common sense knowledge, it's really difficult for me to determine to imagine what is going to happen next. But with LLM, we actually ask the LLM like something like, before I executing the action, I can use my common sense knowledge. I can use the common sense knowledge from the LLM to anticipate what I'm supposed to observe, right? Before I go to the kitchen, according to my common sense knowledge, the fridge, the pots, the plates are more likely to be in the kitchen. While the other things have a small probability that will be in the kitchen, right? So that is naturally for me to sample these more likely branches and should avoid those unnecessary branches that is unlikely to happen. And after that, if I anticipate that I will see the fridge, see the pots, see the plates, and then what am I supposed to do next, right? So this is kind of things is another type of common sense knowledge, except for the imagining what is happening next. We also have the common sense knowledge about how to solve the problem, right? So if I want to go to the kitchen and see the fridge and I want to have some fruits, what am I supposed to do next, right? So according to common sense, I will not likely to move to the bathroom or open the trash can because there's unlikely to solve the problem according to my common sense knowledge. So intuitively, I will choose to open the fridge, right? So this is another type of common sense knowledge about how to solve the problem. So that it's also pretty natural for me to think about, okay, I should open the fridge, and so on and so forth. So the core idea here is that I can use my common sense knowledge to avoid searching some unnecessary branches, because we assume that if our common sense knowledge is correct, which is mostly correct, then I can save my efforts in seeing in searching the possibility that is unlikely to happen, right? So this will be really helpful if the tree is extremely large. So that I can throw away all the other unlikely subtree and only focus on the subtree that is more likely to be true. And this is conducted by the algorithm PUCT. If you're interested, you can search over it. This is the same type of algorithm that used in the AlphaZero. And after that, so that we can put the things together into the Monte Carlo Tree Search. So I can then, in the action selection, I can select the action biasly according to my common sense knowledge. And I can select the observation biasly according to my common sense knowledge. And so on and so forth until I reach the leaf of the tree. And after that, I will simulate to run out to do the random rollout of the plan. Right, so I can generate multiple random actions to see what is going on right after what is going on here, and then back up until and estimate and update my estimated Q value. So this is the whole algorithm. So that this could be very straightforward because it's more likely it's similar to how humans think about, because we will not going to consider about the unlikely things, and we can plan in our minds using the world model, and after that we can execute the action in the real world. So we do the experiments in the simulator environments, for example, in the virtual home simulator, which is very convenient. It does not have the action execution problem. So we assume in this paper we assume that those planning stay at the top at the task level, not in the planning level, not in the low level action execution. And our task is something like I want to rearrange the objects in household environments, and I can instruct the robots to move one object. I can also instruct the robots to move multiple objects using the same instruction. Right. For example, I want to have the fruits and also put the toothbrush into the bathroom, something like this. And we also have some we provide the robots, we provide the LLM with some prompts that is with some examples of the solutions, but we will also test on the task that is not observed in this kind of examples. And we compare the baseline with using LLM as a world model, only use LLM as a world model without any common sense policy to guide the search. And we also use purely as a policy to directly determine the plan given the task. And our experiment actually is quite nice. We can observe that using LLM as a policy together with the world model actually achieve the best performance. And this is our explanation to this kind of phenomenon is that we believe that an LLM world model is actually more accurate than the policy alone, because we assume that if we only do LLM policy, it will not going to consider about, okay, I will generate the plan without considering about the consequences. But if we put the LLM world model together in the search algorithm, I will use the LLM world model to anticipate, okay, if I apply this action, what is going to be the consequences? And using these kind of things to provide me with the feedback so that I can adjust my plan, not only to just simply follow my LLM policy, but I will think about the possible outcomes and using this outcome as a feedback to regularize my plan. So that provides me with a better results. Together, we can also compare with using LLM as a world model without considering about using LLM as a common sense policy. Is that even if we just using LLM as a world model, it will not be able to solve the problem within the time limit, because the search tree is very, very deep. The environment is very, very large. That results in a very large search tree and cannot be solved within the time limits. Right. So why is it so? And we provide with the explanation, which is in this paper we are not going to claim that using LLM as a world model together with the policy that put it into the Monte Carlo Tree Search is the best. It's really determined by the problem you want to solve, right? So so that dropped me a question about, what is the is that to say that using LLM as a world model is better, or using LLM policy is better, or combine it is better? Which is better? So how can we determine this kind of things? So so the problem is so that we consider about using the minimum description length principle to determine which type of solution that you want to solve the problem, which means that a method with shorter description length has a smaller generalization error and is preferred, which is aka the outcomes razor, which is to say that for two solutions, if one solution is very concise and another solution is difficult to describe, then you have to choose the concise solution, which is supposed to be better. And we conduct several experiments to test my hypothesis. For example, like multi-digit multiplication, trouble planning, as well as our analysis about the task. So probably you may have you may be confused about what is the description length. So consider about you want to solve a multi-digit multiplication problem, right? For example, like given a random two n-digit numbers, you want to compute the multiplication. For example, like here, I give if you just directly want to learn the policy to solve this problem directly, that basically means that you want to memorizing all the possible combinations of numbers and their multiplication results. And that is, if this is a policy, then it's going to be a very long policy, because you have to describe the entire table, which is exponential. For example, like each entry is the inputs and outputs, and the entries, the value of the entry is going to be the multiplication result, which is n times 10 to the power of n, which is extremely large. But if you want to consider about the other way, right? So I only need to know the single-digit multiplication results together with the rule to compositionally compute the multiplication. So what is the descriptiveness of this kind of solution? You only need to describe the single-digit multiplication, which is the constant size, together with the algorithm. The algorithm is also be described in the constant size by any reasonable language, programming languages. So that means that your descriptiveness of this solution is a constant. So that means your solution is way more concise than just learning the policy and memorizing all the results. And the empirical result is also suggests that for GPT-4 in 0 shots, if we want to compute 5-digit multiplication, it will have a 0 accuracy. Compared with the one-digit multiplication is a perfect result. So this is one example, and another example is the trouble planning. Right, so this is this is a more like a planning problem, because previous thing is not a planning. It's just simply a multiplication, which is easy to understand, but probably not close to the essence of the problem. Right, so we can consider about the trouble planning, which means that I want to given the starting city and the goal city, I want to find out the path that can travel from the current city to the goal city, right? So if we want to learn the policy, like so memorizing all the solutions, right? The concise description might still be a table, right? So in this table, you will have the input is the current city and the goal city, and the entry of the table, the value of the entry is going to be the next city to fly to. Right? For example, I want to fly from Singapore to New Orleans, and the next city I'm going to fly to might be San Francisco. And after I reach the San Francisco, how can I fly to the New Orleans? Then the solution is just directly fly to New Orleans. That's that. So what is the descriptiveness of this table if we have n number of cities? And we can say that there is n square, which is we have n square entries, and together with the log n. Log n means that I need to describe n cities using the log n bits. So the total description length is n square log n. But what if we want to just simply describe the graph together with the algorithm, right? So that means, well, I can do a search algorithm together with a perfect graph. So if I want to learn this kind of things, what is the description length? So the search algorithm can be described by any programming languages in the constant size. So that is true. And if we want to describe the graph, I assume that the graph is a sparse graph because this is true because in our flights, in our real world, we assume that there is a maximum number of connections from one city to another. So that is, we can approximate the city by assumption that the graph is not fully connected. So the entry should be n log n. Log n means I need to describe n cities, and n means that the number of connections to the one city is actually linear to the number, is approximately linear to the number of cities. So the total description length of the LLM world model together with the search algorithm is smaller than the LLM policy. So that means if we put the LLM world model together with the search algorithm, it will perform better than LLM as a policy. So we also make analysis about our problem, which is object description, object rearrangements, and we also draw a similar conclusion that describing the world model is actually more concise than describing the policy, especially when you consider about rearranging multiple objects. So this is something very interesting. We assumed we can determine what kind of solution that you want to have, and based on the problem that you want to have. Because for some problem, for example, that describing the policy might be more concise than describing the world model. right? For example, like itinerary, you want to travel around the city and you want to determine the itinerary of traveling. And then if you want to do this kind of things, then you need to, if we want to learn the policy, this is going to be something easy because there might be a lot of travel, the posts that share in the internet. There are a lot of posts that first day you need to visit this attraction, second day you need to visit that kind of things, and there is nice food and etc. Those kind of things are massive in the internet. But if you want to learn the world model, that's for example like the traffic connectivity, and also the number, the hotel location, the restaurants, and what kind of things, and also schedule the times that is risen over time. That's going to be very massive information that is required to learn. So it really determined by the problem itself. If the problem determined that a policy is very concise, but the world model is very difficult to describe, then you should choose a policy. And also vice versa. If the world model is more concise and easier to describe, you should use LLM as a world model. Well, for the problem that's in our definition is object rearrangements, it's a bit special because we just realized that even though that the world model is more concise to describe, but the search algorithm cannot solve it within the current time limits. So our solution is that you can probably combine them together, right? Because even though that you want to use LLM policy to guide the search so that you can only search a subtree, and it is still doing a better job because a world model will provide you with the feedback, and you can change you can adjust the plan to make it more and make it better in solving the problem. So that means even though that you search over the neighboring of the policy, the world model still produce you with the better results. So our summary here is that we use large language models as a world model and policy, which combine them together and outperform either one. And we choose the LLM. And how can we choose between LLM world model and also LLM policy? We suggest to use MDP principle. MDL principle, which minimum description length principle, to determine, to analyze the problem and to analyze your solution and select the one that with shorter description length. Okay, thank you very much. This is the end of the talk, and hope you have learned something from this. And I'm happy to take any questions.
Yeah, thank you very much. Wonderful talk. Thank you. Okay, any questions from the listeners? Okay, I have one quick question about the details of the LLM-based searching process. In the figure, it seems that you obtain some kind of probability over the probability distribution over the different actions based on LLMs. Yes. Could you please explain a little bit about how you obtain these probabilities from large language models?
Yeah, so here is that ideally you can extract the token probability, right? For example, I can calculate, okay, move to the bathroom, because I can predict the next token probability. You can use the probability, the log probability directly as a score. Yeah. Another way is that a stupid way, which we did, because at that time we cannot get the token probability from the GPT model. So we just sample multiple times so that I can have a rough distribution over the actions, which is actually pretty deterministic, right? So for example, like we query for 10 times, then the 10 times is open the fridge, or 9 times is open the fridge, and 1 time is to walk to the fridge, or just pick up the apple, or something like this. Yeah, we sample multiple times so that it can have a probability.
Yeah. So when you say this, my first thought was like you directly concatenating the actions to the original prompts and obtain the log probabilities.
Oh, yeah.
Of the outputs. Yeah.
Yeah. Actually, it's correct because we concatenate the previous actions, and then I will predict the next action, and the next action I will sample multiple times and then get a distribution. Or you can just using if you have the access to the log probability, then you can just directly use the log probability.
Yeah. Another question is, have you encountered any problems when utilizing large language model as knowledge bases, such as hallucinations? Are these problems deeply, affect the performance of these systems?
Yes, of course. So we have one assumption that is that the world model, the LLM world model, and LLM world model is a reasonable approximation to the real worlds. Right? For example, if the world is very different from the LLM's anticipation, then that means you have a model error, and your feedback from the world model is wrong. So how can we solve this? We actually solve this by using because every time you execute real action in the real world, you will receive a new observation. That is something real. This is a correct feedback from the real environments. You can use this new observation from the real world to update your belief about the environment. So that, as you can see, that we only provide you with the prior belief about the environments. So if the belief is updated by the real observation, then there is a belief updates procedure. I think that I didn't put it up here because there is a belief updates from we only provide you with the initial belief using the LLM, right? So take the example of here. What is the possible position of the fridge, right? So this is the only one time query, right? So you have, for example, like 90% in the fridge and 10% in somewhere else. And then this is a prior belief, right? So after that, when I really enter the kitchen and I see nothing, and then my belief of that the fridge in the kitchen should be 0 and other places should be higher, right? So this is the real-time updates. So after that, I will have a new belief, right? So, and then I will sample the position from the new belief and the procedure, then to proceed my planning. And then over time, if I execute long enough time, then I will have a better estimation of the real world. So I will have a more accurate knowledge about the environments.
Okay.
Right. So this is the one thing. Yeah. Another thing here is a policy error, right? So because the policy is not perfect, sometimes it will explore the wrong direction. So our for now we did not do anything to let it do better because we assume that if we provide them with a new observation, they will, not going to do stupid things. But sometimes it's still repeatedly doing stupid things. So I think that is this part. How can we make this search algorithm? For example, I stop repeating the stupid things. Is still. I think that there might be some smart solutions, but we did not explore it.
Yeah. Yes, that's also what I think about, because you have from my understanding, you have a fixed action space, right? In this pure search-based algorithms, but if you utilize the generalizability of large language models, it may provide, in some unseen conditions or unseen scenarios, it may provide you with some unseen actions. May provide you with because it is able to generate this more generalizable actions. So it may provide you with more options in these unseen scenarios. So maybe I think that may be another direction for future development of further utilizing large language models for these searching problems.
Yeah, I think that's your problem. If I understand correctly, you want to solve. That is going to be very useful if we want to solve the open world problem, because for now we have a closed domain. We have everything that is state space is defined and action space is defined. But what if I want to, explore, because our world is an open world. We assume that it's open world, and there will always be new things and probably new actions associated with the things. Then Yeah, I think that is a still open question, because the open world problem is, I personally think that if you want to solve open world, then you shouldn't have the predefined states, or you should have some dynamically changeable states.
Yeah.
That is something revolutionary, because we think that for now the algorithm still assume that there is a fixed definition of the states, fixed states. Yeah, I think so, because but I do not have a good idea in my mind to solve this problem properly. But I think that's your point of view is correct. I think that LLM is a possibility, that is a game changer here to help me solve.
I think it might be very interesting because, for example, if you like in a new scenario for new task, we also combine the original Monte Carlo search algorithm with LLMs. For example, in one state, when you perform this kind of probability calculations, and you find the confidence is very low, because for all the existing actions, the probability is very low. So maybe you can ask LLMs to provide you with a new actions that is unseen or undefined in the action space. It may, solving the problem zero shotly better.
Yeah, I agree. Yes, that's actually but I think that if you want to put this into the classical algorithm, I'm not sure whether there is an unknown problem, but I think it's going to be a very exciting direction to explore.
Yeah, definitely. Okay, that's all my questions. Do you have any other questions from the other participants? Okay, thank you very much, Zirui, for a wonderful talk. Could you please share your slides with me after this talk?
Sure, no problem.
Okay. Thank you very much.
Okay.
So that's it. Thank you again, Zirui, and for all the participants. Thank you. Bye. Have a nice weekend.
Thank you. Bye.